Hello and welcome back. Kaylee here. Hopefully you have a pretty good feeling for how that implication truth table works. If not, we're going to talk about it a little bit more here, and you'll explore implications more in the homework this week. Speaking of homework, this is going to be one of your homework problems. So this is, when I was mentioning that book, The Math Gene, this is the puzzle that's actually presented in the psychological testing that was done that Keith Devlin used as an example. And so this is the one that people tend to struggle with, and I will admit that when I first read the puzzle, I got it wrong. So don't rush into this puzzle. I think it kind of is deceptive and looks like it's easier than it actually is. So just take your time, think about it, don't rush, and think back to that party example, because it's the same thing. So if you can connect the hypothesis and conclusion here of this rule that this game is following, then you'll be able to figure this out with no trouble. So think about a card being or having a vowel on one side. Think about that in the same way you thought about guests drinking an alcoholic beverage. Think about the conclusion, an even number on the other side, just like the conclusion in our party example. Guest must be above the legal age. If you follow that and try to take away this abstraction here, get it closer to something that you can imagine yourself being in, that party situation, you'll get it with no trouble. Okay? So just try to compare those, try to do those, and I might do a couple different 4-card examples for you, and then you have to indicate which one you would have to flip over. So think on that. It'll come up again on the homework. I just wanted to give you a heads up so you can start churning about this puzzle. This is the truth table for the implication. Hopefully you were able to either research and figure out these truth values, or you use that party example and you were able to put together these truth values. When you're looking at a truth table, it's nice to kind of take note of what's going on and when it's true, when it's false. And so the way that I remember the implication is that the only time it's false is if I have a true hypothesis but a false conclusion. And so I think this kind of makes sense, hopefully. And it really makes sense if you think about the drinking one, because remember with our party example, this would mean that the person was drinking, but they weren't of legal age. So this would be the only situation where an issue would arise, because if the person's drinking and they're legal age, we don't care. If they're not drinking, they are of legal age, we don't care. If they're not drinking, they're not of legal age, we don't care. So the only issue we're going to have is if they are drinking, but they're not of legal age. So some people connect it to an implication like that to really wrap their head around it. Some people just remember that the only time an implication is false is when the second conclusion is false but hypothesis true. So true implies false is false, otherwise that implication is going to be true. And again, we're dealing with these little atomic propositions now, but eventually we're going to have 8 rows going on in our truth tables with more compound, complex implications. So it might seem easy to read true, 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 true implies true is true, but imagine getting more rows going on and having more columns to keep track of. So you want to remember this basic one because we're going to be expanding it. And again, just some vocab here. And again, in this class, you don't have to worry too much about vocab, but they will be terms that'll come up either in lectures or other videos from other places that I might post. So it's just nice to kind of get a handle on these and have them in your notes available. One practice that's really good is a notation page. And so every time you see a symbol or a vocab word that you don't know, go ahead and write it down on your sheet of paper so you've got all the symbols and vocab and things that you want to have on hand. So probably like any symbols that you aren't familiar with, the basic connective truth tables that we've talked about, so and, or, exclusive or, implication, and biconditional negation. So make sure you keep all those things straight. So if we're in an implication here, this is our hypothesis, our conclusion, and sometimes it'll be referred to as antecedent, premise, consequence, depending on what text you're looking at or what site you're looking at. This is really important. So this is kind of what I was hinting at when I was talking about all those rows and columns in our truth table growing a little bit. The order of the implication, the order that that hypothesis and conclusion comes in, is important. If you notice when you were answering which implication applies to that party situation, it was different for us to say, if your guest is of legal drinking age, then they must be drinking. That was different than saying, if they are drinking an alcoholic beverage, then they must be of legal age. So think about those two implications. Maybe go back to the quiz and look at those ones that you had to choose from, and notice how they're different and they mean different things. So we're building to this idea of logical equivalence. So the way that we can prove logical equivalence, one way that we're going to develop this week, is by just using the truth tables of each of the compound propositions. In this case, we're looking at the compound proposition P implies Q, and the compound proposition, or cis conditional, Q implies P. And the way that we show that two compound propositions are not logically equivalent, we just have to show that just one truth value differs. And notice our columns are the same, okay? If I changed this guy and named him Q, and this guy and named him P, then these would be in the same order as this, but it wouldn't be able to be interpreted the same way. I'm not sure if you understand what I'm saying. What I'm saying here is make sure that your propositions, your atomic propositions that you're starting with, are in the same order for each of the propositions you're trying to compare. Okay, so I'm trying to compare P implies Q to Q implies P. So I want to make sure that my first two columns of all the possible truth value combinations of these atomic propositions are in the same order. So what's best usually when you're trying to think about logical equivalence is to just, put a little additional column here. Don't try to write out your atomic propositions again, because you might make the mistake of reordering them. Just go ahead and put on one more column here that says Q implies P, and then make sure you're doing true implies true is true, false implies true is true, true implies false is false, false implies false is true. Okay, so notice how we get different truth values here. So we know these are not logical equivalent. And in the next little segment of this stuff, we're going to see what it looks like when they are logically equivalent with truth tables. So these truth tables here tell us that the order of implication matters. And I think symbolically it's kind of telling you that, right? On this side, there's nothing. On this side, there's an arrow. With and or, I wonder what's going on with that. Does order matter? So is P and Q logically equivalent to Q and P? Think about that. Post on the discussion boards. Ask around. Google. Well, first post, what's your intuition? Is P and Q the same as Q and P? Is P or Q the same as Q or P? Is P exclusive or Q the same as Q exclusive or P? So think about that. All right, this is kind of a weird thing with this implication, and the way that we use it in logic is there doesn't have to be any connection between P and Q, and we can still make a statement about it. We can still determine if that statement is true or false. As long as we know that P and Q are propositions and we know their truth values, we can determine the truth value of this implication, even though it might not mean anything to us at all, okay? But we're just, speaking logically and kind of backing up from the English a little bit and trying to move to just logic. So see here. So, for example, these guys don't make any sense if you would tell them to your friend or something that if they weren't in this class. But we can actually say that all three of these statements are true. And I wonder why. Why is it true that if the moon is made of green cheese, then I, Kaylee Gray, have more money than Bill Gates? I will tell you, the moon is not made of green cheese. That is false. And I do not have more money than Bill Gates. That's false. I'm not on welfare, though. The moon's not made of green cheese. 1 + 1 = 3. That's false. That's a false proposition. Your grandma wears combat boots. Well, let's just say my grandma Barb. She doesn't wear combat boots, but maybe your grandma Barb does. But I'm going to say, well, maybe your grandma's not Barb, but your grandma, maybe she or your mom or your sister, whoever you want, wears combat boots. But I'm going to say, no matter whose grandma we're talking about, whether this proposition is true or false, this is still going to be true. So post on discussion board. Tell me, why are these three guys true, no matter what? I put up a screenshot of this slide just so that kind of a heads up when you're seeing different conditional statements, different ways that it might be written. So just make sure that you're aware of these, and might come up in a quiz or homework, so that screenshot's there. I'm not going to go through all of them, but notice, depending on how you're saying it, you might list the hypothesis and the conclusion in a different order. So just pay attention to that. Don't automatically assume that the first one that's written down in that statement you're reading is your hypothesis. And this will be really important if you're given a mathematical statement that you have to prove. You have to know what your hypothesis and what your conclusion is. If you don't, or if you choose the wrong hypothesis and conclusion, then you're not proving the same statement. Remember, P implies Q is not the same as Q implies P. So make sure to think about that. All right, we're ready for a new connective. And really, this is nothing crazy here. This is just our connectives that we already know joined together in a bigger compound proposition. And then, you know, we love notation and symbols, so we're going to create a new symbol just to simplify our work. So your job in a quiz on D2L and on the homework, you're going to build a truth table for this other representation of a biconditional. A biconditional is just two, by two conditionals put together. So we've got two propositions. They might be compound, but in this case they're just atomic, nothing crazy, P and Q. We've got the forward implication and the backward implication, just like the arrows tell us. And I wonder, guys, is this connective commutative? Because remember, this implication is not commutative. P implies Q is not the same as Q implies P. And just to kind of give you a little bit of heads up on some of the statements that we'll be proving, a couple of examples of if and only if statements. We'll be proving that for any integer, if that integer squared is odd, that is true if and only if the integer is odd. And another example, 3 times some integer n plus 2 is odd if and only if 9 times that same integer plus 5 is even. And the way that we're going to be proving these examples, we're going to develop a lot of tools first to prove just atomic propositions, just singular statements like square root of 2 is irrational. There's no connective there. And then we're going to add connectives. Mostly we're talking about conditionals. So we're going to be talking about how to prove conditional statements. And then we're going to talk about proving biconditionals. And really, just like this new connective, it's not really anything new, right? Because we're just taking connectives we already know and putting them together in a longer statement. And it's going to be true when we try to prove biconditional statements, because we're really just going to be proving 2 conditional statements. All right, so your goal for the homework and for D2L is going to be to write a truth table for this biconditional using this different representation, okay? You shouldn't know yet what the truth table of this is. If you do, then just fill out the thing and go on. But you will have to make the truth table of this compound proposition, and if you already know what the truth table of the biconditional is, then those truth values should line up. As we talked before, these are logically equivalent. So P, if and only if Q, is logically equivalent to this, okay? We're going to talk more in a little bit about order of precedence and more setup for the truth tables. So keep that in mind. Notice that we've grouped some things by parentheses here, and that's important. So pay attention to that. So go ahead, do the biconditional quiz on D2L, and do that truth table of the logically equivalent representation of the biconditional, and then come back and we'll talk about converse, contrapositive, inverse, truth tables, order of precedence, logical equivalence. So we're almost done. Yay! We're almost done with the week. Okay, I'll talk soon. Bye.